Okay, today we're going to have a look at how to use ferrite. During my consulting career, I often travel to test labs with my clients, and I work very closely with test engineers, both experienced ones and those engineers who just get into the practice. And one thing I found was that some of the test engineers, especially the young test engineers, when they wanted to suppress common mode noise on a cable structure, what they often do is they just go to the drawer or the cabin where they store all different kinds of ferrites. They pick up one and then they use it without knowing, the type of material he should use, or the size of the ferrite. Often these details are overlooked. So the purpose of this video is to sort of educate those engineers who are not so familiar with ferrite. So as you can see here, we have a selection of ferrites just showing here from different manufacturers. I often use these types ferrites from Ferrite. You can see now they have the new part where they put the part number on the plastic housing, which is quite handy because you can see here it says 0461, and that 61 often indicates the material. This small one, very tiny, right? And it's from TDK, as you can see. Also, you can find, if you look closely, yeah, there's a parts number here, if you can look at that. And for example, this one, I only use it to clamp on a cable, so to suppress a broadband noise up to 1 gigahertz. So you can already see the difference, right? Whereas a ferrite part depends on the material. So for example, 6.1, I have the frequency range written here, 100 megahertz to 1 gigahertz. And of course, for lower frequency, they have the 75 material and 31 material. Depends on the size of the cable. Of course, you can go for these very big size ones. These are from Worth Electronics, of course. You can also see from the mechanical design point of view, for example, Worth Electronics, all their ferrites, you need to use a key to open it, right? So it depends on if you're a person who prefers to use the key or not. But of course, using key has its own benefits, because the argument would be when you clip the ferrite core, the gap between the two ferrite cores is well controlled. You also get these type of flat ones, right? And you can already see, yeah, the depths and the height, or shall we say, of the aperture is quite small. So these are often used if you have a ribbon cable, for example, and then you clip this on the ribbon cable. So that's the ferrite solution. Again, 31 material, works up to 250 megahertz. Okay. And this is the Worth Electronics ones. Okay. One thing I wanted to point out now is, as you can see, I wrote the numbers here. So for example, this one is a 31 material, and it starts working from 1 megahertz. At least that's where the manufacturer starts providing you the data. But you can see at 1 megahertz, it's quite small, resistive, right? Because all ferrite materials are resistive. We'll explain that in detail. But this one is quite low resistive, 14 ohms at 1 megahertz. As your frequency starts to increase, you start to get more resistive components out of it, right? So for example, this one, when it comes to 250 megahertz, now your resistive value is 440 ohm. So what does that mean then? That means, well, this one, if you have some noise, for example, sits like 200 or 300 megahertz, then yeah, this perhaps is the correct material you use. But for example, if you have hundreds of kilohertz of noise, yeah, forget about it. This one will never work in that frequency. You choose another type. Okay. Okay, so let's get the basics. The way a noise is generated, particularly if you have a cable linking two equipment or two devices. So in this case, if I draw a equipment A and equipment B, or could be PCB A or could be PCB B, and then they are often connected using cable structures, right? And suppose you have a common ground in this case, and when we say common ground, it could be anything, could be earth, could be equipment ground, could be your chassis, and depends on the noise frequency. Inevitably, you will have some impedance between your A and your ground, and also you will have your B and your ground. So if we represent it in a very simple circuit, we can sort of draw a noise source, and we know this noise source is frequency dependent, and this noise source often has a impedance, which also, the fact that we call it impedance means it's also frequency impedance. But in this case, for the purpose of this demonstration, we just draw a resistance component, okay? And then we can sort of draw the receiving part, let's say, of this circuit is also a resistive component, but we know in fact often this is impedance, so this is really frequency dependent, okay? Depends on frequency. Same applying to this source impedance. And what happens is, okay, so this is our cable linking the two circuit, and this perhaps is the ground, we call it common ground. So often depends on how you bond or connect the circuit to this ground. You can, for example, you could have a direct connect either through a braided wire, or it could be the pillars and screws to pillars and connected to the PCB. All sorts, right? So you could have a direct connect, or you could also, in this sometimes you don't have any connection. But if you don't have any connection, you still have some capacitive connection there. And we all know that the impedance of a capacitor is 1 over 2 pi fc. Therefore, when it comes to 10 megahertz or 100 megahertz, this impedance can be very small. So this impedance can be very small. Okay. So knowing these basics, when we apply a ferrite, okay, so in this case, let's just put a ferrite core somewhere here, okay? So this represents my ferrite. If you check the data sheet of ferrite, you will immediately see that often the data sheets provides you a impedance against frequency curve, but often that impedance is very close to the resistive value of the ferrite core material. So often it has a sort of shape like this, okay? So it means a ferrite, if we want to treat it simply, a ferrite, what I often call is a frequency dependent resistor. So I write it like this. So it's really more resistive rather than inductive, and also it's frequency dependent. Therefore, I call it frequency dependent resistor. So knowing this, let's have a look at why it is important to understand the impedance of the source and also the impedance of the load. Okay, so let's have a look. So let me raise this bit off. If you have the data sheet, let's just say in the first case we have at certain frequency, let's say at 100 megahertz, at 100 megahertz, okay? So we're saying at 100 megahertz, then we have, at this particular frequency, our source impedance tends to be showing as 10 ohms, for example. And our load impedance, again, is 10 ohms, okay? And if we use a ferrite and we check the data sheet and it says 100 ohms at 100 megahertz, so that's the resistive value of the ferrite. So in this case, if we can calculate the attenuation, we call it attenuation, basically it's like insertion loss, isn't it? So our attenuation, again, often is in log terms, so it's defined as 20 log 10, right? And how do we calculate? Well, we're based on the math, like, you got 10, 10, so I put 10 plus 10, and then now, so this is before I insert the ferrite, and now I insert the ferrite, so now the equation, it becomes, on the denominator would be 10 plus 100 plus 10, okay? So if you work out the math, this would give you about minus 15.6 dB, okay? So I'm not showing the math here, but this is really the result, minus 15.6 dB. which means if you have a circuit at 100 megahertz and you got noise at 100 megahertz, then putting this particular ferrite, you will achieve roughly 15 dB reduction. So that's quite good. That's quite good. Okay, but this is really based on a scenario where you only have 10 ohms and 10 ohms. Okay, what if you have a different value? So this is what we call low impedance circuits, right? On the noise, on the source side, which is PCBA, and on the low side, PCBB. So say if I had 100 ohms rather than 10 ohms, and I also had 100 ohms here, then my attenuation, so called attenuation dash, using again exactly the same equation, log 10. So, but in this case, I have 100 ohm plus 100 ohms, and then divided by 100 plus 100 plus 100. This would give me about minus 2 dB, minus 2 dB. Okay, so you can see now, same ferrite core, whereas in the previous case, I have about 16 dB, but now I only got 2 dB. If you only got 2 dB attenuation on a common mode current, and you're measuring a far field using antenna, this 2 dB reduction might not give you sufficient suppression to suppress your loads. Okay, so this, I guess, this is the basics of ferrite core, and actually lots of people don't understand this. So in conclusion, what we learned today is when using a ferrite, you need to look at the impedance or resistive value at certain frequency, and often that's the frequency you want to suppress noise, and really trying to understand your circuit, right? Because your circuit could be low impedance at one end and high impedance at the other, or it could be high or low. But the fact is, we don't know. We don't often know the circuit, especially if we're test engineers. We have no idea what the design engineers got here. Okay, so how do we cope with it? Because we don't know the circuit and we only got ferrites. How do we use it then? So that will leave to our next session, where we're going to use a very interesting demonstration kit, and I'll show you how we can really see this in reality. So I'll just give you a quick look at this demonstration kit, and you already see, right? We have some interesting resistive network where we can use a low impedance network and high impedance network, and then I'll connect this to, again, to my VNA or spectrum analyzer with tracking generator, and we will have a look at different ferrites on different impedance network and see the result. Okay, so I hope you enjoy this basic lesson of ferrite cores, and definitely check out our sequel episodes on the ferrite cores. We probably because that one we will do some demo as well. Okay, and you may already notice I have this cards here, which can give you 20% off if you go to the EMC and CI conference in Newbury this year in UK. I am one of the organizers trying to really push this conference to the wider electronics engineer, because I truly believe this is a good opportunity if you are a design engineer or test engineer, or engineers working in a high frequency field. You want to really meet people, share experience, and learn something, then this is really the conference to be. So yeah, definitely check it out. And if you want to, either get a conference ticket or a trainer ticket, you can always use this promotion code. Or if you just want to exhibition stand, go there. You can win prize. Apparently, I think lots of companies are putting very appealing prize. So yeah, definitely go there and have a look.